Hey gang, for this section of lectures we are going to talk first about limiting reagents, which means we're going to be doing a little bit of math, and then we're going to hit reactivity trends. This will be something of a recap. Hopefully it won't throw too much or maybe even any new information at you, but we'll just go back over the way the different groups on the periodic table react. But first, the math. Limiting reagents is more about stoichiometry. Basically, if you're given different quantities of the reagents, how much product can you form? That's based on how much of each is present. One of them will be present in an excess amount. The other one will be the limiting reagent. For example, if you were making bicycles, you need a pair of tires, 2 tires. You need a frame, 1 frame, and you need a handlebars. 1 set of handlebars. For every bicycle you want to make. So if you have, 7 tires, 3 frames, my writing got awful there, and 3 handlebars, how many bikes can you make? 3 frames would require 3 handlebars, would require 6 tires. Okay? So these two just happen to work out nicely to be the limiting reagents. This one here is present in excess. You can make 3 bikes with your 3 frames, 3 handlebars, and 1 tire left over. So that's really all there is to it when it comes to limiting reagents. You're just finding out which of your reagents, just another word for reactant, which of your reactants is going to be the one that there's not enough of, which one is going to run out first as you move forward. So once again, you're going to convert to moles. Never work in mass. Never, ever, ever. If you react, for example, 5 grams of hydrogen with 20 grams of nitrogen, how much ammonia can you make? Let's go ahead and write out and balance the reaction. So nitrogen plus hydrogen yields ammonia. Balanced, we have 20 grams of nitrogen, 5 grams of hydrogen. How much of this can we make? So step 1, convert to moles. So divide 20 by 28.01 grams per mole. 0.02. That's a molar mass of molecular nitrogen. And you divide hydrogen by 2.016 grams per mole. That gives us 0.7138 moles of N2 and 2.48 moles of hydrogen. You might be tempted to think that the nitrogen is the limiting reagent. There's obviously less of it. You would be wrong. Well, wrong-ish. Because we're not done yet. We need to do our stoichiometry work first. Because we need to take into account the fact that, there are 3 moles of hydrogen needed for every 1 mole of nitrogen. Before you can do this, you need to divide by stoichiometric coefficient. That just means divide by the number up here. Divide by the number in front of the element. So you're going to be dividing nitrogen by 1, you're going to be dividing hydrogen by 3. And essentially what you're getting here is how many times the reaction as a whole can proceed. You're just finding a relationship between the quantity and the reaction. Okay. So once you do that division, you get 0.7138 for nitrogen and 0.827 for hydrogen. This number down here, basically what we've done it's a mathematical calculation whose only real purpose is to give us the limiting reagent. What we have here, just these two numbers that tell us how much is available for the reaction, and that means that the smaller number is always going to be the limiting reagent. The larger number is always going to be present in excess. Doesn't matter what the reaction is. It doesn't even matter if you have 3, 5, or 29 reactants. If you have too much stuff, then you have too much stuff. Whatever is the smallest number for this calculation is going to be the limiting reagent. You can have different quantities present in excess. You can have something that has like 2,000 times too much and one that just has a little bit too much, but they're both in excess. Okay, the smallest number in this calculation down here is always going to be the limiting reagent. That's all this is used for down here. This is only for finding the limiting reagent. Once you've found the limiting reagent, you come back up here to the middle and you use the moles of stuff. You don't use these things down here. No. You don't use those for further calculations. So you move forward with these. Okay? You always use the moles. Okay? Down here at the bottom, only for limiting reagent. I want to specify that because a lot of people sort of get messed up on that. They sort of get confused on that. Now, once you've found the limiting reagent, then you can move it forward. You can find out how much product you can make. So, 0.7138 moles of nitrogen. And we're trying to find out how much ammonia we can make. So, 2 goes on top. You make 2 moles of ammonia for every 1 mole of nitrogen you consume, which means that the most you can make using this setup, 20 grams of nitrogen and 5 grams of hydrogen, the most you can make is 1.428 moles of ammonia. And very often, not necessarily always, but very often, I will ask you not for the moles, but what mass of ammonia or what mass of product you can produce. Mostly because I think it's good practice to just keep on doing the same thing over and over again. So you need to multiply the number of moles by the molar mass of ammonia, which gives you 24.33 grams. And that makes sense, because it's going to be the 20 grams of nitrogen plus a little bit less than the full 5 grams of hydrogen. So you should expect it to be somewhere between 20 and 25. Let's go ahead and do another example. Let's make something up a little bit. Let's go ahead and say we're making calcium carbonate using the pure elements. So solid calcium plus solid carbon plus gaseous oxygen, combining in a very improbable fashion to make calcium carbonate. So we would need to double this, triple this, and double each of these. Now we have a balanced equation. So let's say we had, let's make it interesting. Let's make it simple actually. 10 grams of calcium, 10 grams of carbon, and 10 grams of oxygen. Which one is the limiting reagent? First things first, convert to moles. So you divide calcium by the molar mass of calcium. Calcium, boom, is a molar mass of 40.078. Carbon has a molar mass of 12.011. And oxygen has a molar mass of twice that, or 31.998. And then you convert those to moles, and what do you get? The moles of calcium is 0.2495 moles, and you have 0.8326 moles of carbon and 0.3125 moles of oxygen. Those are numbers that you would use going forward to find the amount of calcium carbonate you make, but before you could do that, you need to find the ratio. You need to find out which one is the limiting reagent. So you divide by 2. Let's not obscure the numbers. And you divide carbon by 2. And you divide oxygen by 3. And when you do that, the numbers you get are 0.1248, 0.4163, and 0.1042. So that means that for this particular reaction, oxygen is the limiting reagent. Both calcium and carbon are present in excess. And this is the one that will run out first, oxygen, which means that if we're going to calculate the amount of calcium carbonate produced, we would have to use the number of moles of oxygen to do that calculation. Okay, so that is how you find a limiting reagent. Reaction yield. Now, in an ideal world, a reaction would always produce 100% of what it could produce. And in an ideal world, my cats would not fart when they jump up on my lap. We have two different quantities here. The theoretical yield is how much product you should get. The actual yield is how much you do get. And the percent yield is just, the percentage between the two. Just actual over theoretical times 100%. And the job of a chemical engineer is to scale up the chemist's work to get from grams to tons and to maximize percent yield. Okay. So they can, get a really, really cost-effective industrial strategy. Let's go back to our example here with nitrogen. As you'll recall, we had 5 grams of hydrogen and 20 grams of nitrogen, from which we get the theoretical yield of 24.33 grams of ammonia. Now that's what we calculated. That's what you can expect as the absolute maximum. Okay, that's the theoretical yield. And you cannot exceed that because you don't have enough nitrogen. If you actually produce 21.27 grams, what is your percent yield? So that's one way to give you a percent yield problem. Now, I could give you a limiting reagent problem that would let you figure out the theoretical yield. Then I could give you the actual yield and ask you to calculate the percent yield. Really simple. Percent yield is actual over theoretical, or 21.27 grams divided by 24.33 grams is 0.8742, or 87.42%. That's really not bad. Now, where did the other, 13% go? What happened to the other 3 and a bit grams? Well, there are a couple of problems. First, in order for, reactants to react, they need to actually collide with one another and spit out products. But that gets harder and harder to do as you get fewer and fewer molecules of the reactants. They can't interact physically if they're separated by, even a couple of centimeters. Okay, in molecular terms, that's pretty much infinite distance. So as you start getting toward the end, the reaction becomes less and less likely to happen just because you have less reactants. Another problem is that you don't just have the one reaction happening. You can get side products or side reactions. That is to say, just because, you expect ammonia doesn't mean that's what you're going to get. You could get N2H4, for example, hydrazine. That's really unlikely. This is rocket fuel down here. But, it's possible. For other reactions, you would have other side products, of course. And, the more complicated the reaction, the more steps it has, the more reactants it has, the more side products you can get. So that's another thing that can drain your percent yield. Finally, a lot of reactions aren't really, so straightforward, going from A to B. A lot of reactions actually look like this. They are what are known as equilibria, or they exist in equilibrium. Okay, reactants react with one another to form products, but there's nothing really that tells a chemical it's a product and not a reactant. The products can react with one another to go back in the reverse direction. So a lot of reactions, technically all reactions, exist in some form of equilibrium. It's just that some of them, the reverse reaction, it makes up a very, very small portion of the overall balance. Hydrogen and oxygen react very, very easily to form water. Water is very, very unlikely to go back in the reverse direction to form hydrogen and oxygen. It could happen, just very unlikely. But some reactions, you get this sort of equilibrium much more easily. And it's the job of those chemical engineers to try and get rid of one of those arrows. But there are a lot of different things that can steal away your 100% yield. That gives us 3 numbers to play around with: your actual yield, your theoretical yield, and your percent yield. So I can give you any 2 of those numbers, or the ability to find any 2 of those numbers, and ask you to calculate the third. I could even ask you something wild and complicated, like for the nitrogen plus hydrogen yielding ammonia reaction, given, an 83% yield, and the desire to produce 500.0 grams of ammonia and an excess of nitrogen, how much hydrogen do you need in grams? That seems incredibly complicated, but you can, in fact, solve it. And I'm going to give you that on homework, if I haven't already. And that will be that when it comes to this particular lecture. And we'll also do it for math for this set of slides. When we come back in our next lecture, we'll be talking about the chemical reactivity, the chemical properties of some of the groups on the periodic table.